Thanks. So my name is Christian. I'm the author of the load store pair for RV32 fast track extension. And in this talk, I'm giving you a little bit of an introduction and some results regarding the extension. So I want to start off with an overview of where we are with this extension. In a nutshell, the load store pair for RV32, like the name suggests, adds the capability to load or store a double word using aligned register pairs, and I'll get into the details of that in a minute. It is RV32 only and reuses the existing RV64 encodings for load and store double. You see some important links regarding the most important resources on the specification. This is a specification which is not yet ratified. In the life cycle, it is very close, but not yet at freeze. So it's a stable specification, but it has completed the architecture review. We've also checked pretty much all the freeze items. What's missing is the voting by the tech chairs, etc. And we'll kick that off after the summit. So then very soon, I'm hoping that we can also start the public review. If everything goes to plan, roughly the public review would end in December. So watch out for the public review if you want to check out the specification and contribute to that. So this is coming up. In that timeline, we could achieve the ratification in February next year. So it's not too far off. Some background on the extension. So I mentioned we're using aligned register pairs, also called even-odd register pairs, and they're being used mostly in cores for embedded systems. They can boost your performance, at least if you have a 64-bit data interface, otherwise not, but they can definitely also reduce code size. There is currently one ratified extension which is already making use of those aligned pairs, and that is ZD in X, so double precision floating point in the X registers. There is another specification coming up which will make use of these pairs, and that is the packed SIMD capital P extension. Now, none of these extensions actually have the capability to load or store a double. So we felt it was really important to add that capability to the ISA. As actually in many of such applications, you might really have a memory bottleneck, which could be solved with this application, again, if you have a 64-bit data interface. Otherwise, the bottleneck doesn't change. I've listed some examples of existing ISAs that already make use of the even-odd register pairs. So we're not inventing anything here, just applying it to the RISC-V ISA. Now, how are even-odd register pairs defined in RISC-V? The definition comes out of the ZD in X specification. And that applies actually only to the RV32 version of ZD in X. Otherwise, you have 64-bit registers for RV64. Aligned register pairs means that in your instruction, the register number of the operand must be even. If it's an uneven number, that is a reserved encoding. There is a special behavior around the X0 register. So if you write to X0, your write will be ignored. It's not just the one half is being written to X1 and X0 is ignored, and the entire thing is ignored. When you're reading from X0, you're reading 0 altogether. So you're not reading that one half of X1. That gives you to a register map that is basically one big 0 register of 64 bits, and then there is 15 register pairs. So some background on the design of the extension. So it is RV32 only. There's a few reasons why that's the case. It could, in theory, also be done for RV64, and we could apply the same principle of reusing the encodings of the bigger extension, which would be RV128, which does have load and store quad encodings, or instructions at least, but the encodings actually don't exist. And also for RV64, we might go a different direction if we wanted to add load and store pair, because those even-odd pairs, they don't always mix well with out-of-order designs that do renaming. Another important thing is that we do allow non-atomic implementations, and that translates at the end of the day to we allow implementing this extension even if you only have a 32-bit memory interface, then you need to break it into at least 2 transactions. So it cannot be atomic, but we wanted to allow this because it may bring code size benefits to other smaller microcontrollers. It's pretty similar to the ZCMP extension, which is the push-pop, which also cracks the push and pop instructions into multiple load stores. Due to the extensions that it works with, it's clearly focused on embedded microcontrollers, less so application processes, also pretty clear from the fact that it's RV32 only. There are other ways that you can do load store pair, and this T-head mem pair extension is an example of that. Instead of using an even-odd pair, you can basically specify each register of the pair individually. Of course, it's more flexible. You could find more opportunities to use that instruction. But of course, an additional register means also you need more encoding bits. And we prefer to use those encoding bits somewhere else, for example, for a longer immediate. Or, and that's the cool thing, if you use the even-odd pairs, you can have the compressed encodings. And that's where the real code size benefits come from. One note, if you had looked at the specification at a previous point in time, the compressed extension, which is now called Zclsd, used to be called ZCM-LSD. The M indicating that it does overlap with an existing compressed extension, and that is the single precision load stores, which you don't need anyway if you do ZFNX, ZDNX, and which do overlap with the RV64 load double and store double encodings. The M was removed in order to have mnemonics that are C.LD and C.SD, so that it is the same mnemonic as for RV64. That's the entire background why it was changed. This is just an overview of the encodings. So you see there are 2 encodings in 32-bit or 2 32-bit encodings. This is the ZILSD extension. It's the same encoding as load double. Difference being, if you, for example, look at LD, the destination register, it's required that the least significant bit is 0. So technically speaking, actually, we're not even using the entire encoding space of load store double for RV64. We're only using half of it. The other half is still reserved. Below, you see the compressed encodings, and it's the same story. So that is the background on the extension. In the next slides, I want to share some results, in particular on the static code size, but also instructions retired as a proxy of performance, potentially also power. I used a number of benchmarks. Most of the results that you will see are on mbench because it works quite well for measuring code size reduction. I think it's the most prominent benchmark for that case. A bunch more fine print on the compiler and linker options. Importantly, we did include ZCE, and ZCE includes push-pop. If you don't include push-pop, then load store double is also really good at optimizing prolog and epilogue. But in the use cases we're looking at, it's very, very likely that you do have push-pop. So we didn't want to make our results look too good. So ZCE is included. So I don't have any gains from optimizing the prolog or epilogue. If you didn't have push pop, probably for all the results I'm showing, you can add another 3% code size reduction. ZDNX is always included, also to avoid that we have any soft float libraries included. Compilers, most of the results I show are on LLVM 18. You will also find the prototype of that. It's all open source. Also GCC, although with GCC we had the issue that bin utils, I don't know if it's still true today, it was still true like a very few weeks ago, does not support ZCMP. So we couldn't compile it all the way through with the ZCMP. So we did work around that limitation, but it's there. So this is mbench, static code size reduction. It's compiled for OZ. And you see there is a number of different benchmarks. Some show a really great code size reduction of more than 25% at the best. These are typically benchmarks which have some exposure to double precision. That means there are variables that are simply doubles. So of course that makes it very easy to optimize. There is one benchmark in there which is also showing pretty good performance, which is the Wikisort, which has this black bar behind it. It doesn't use double at all, but it uses structures which are 232-bit integers. And of course, you can also load and store that perfectly with the extension. So that is also showing pretty good effects. There's some workloads where hardly any load store double instructions were used. Unfortunately, we still have some cases where the code size actually expanded. So that's simply, I think, due to the compiler not being very optimized yet. Yeah. This is over a wider range of benchmarks, and you will see that actually the code size reduction is a lot less. It's still okay-ish. I mean, you still get, like, I think on average it is 1.76% of code size reduction. But also these benchmarks do include a lot of library code that is not optimized for ZCLSD, so you could actually improve that quite a bit. And in many cases, you know, those benchmarks, they will include a bunch of printf code and so, which is anyway not realistic for the application, and that sort of skews the results a bit. So in reality, it's probably a bit higher. This slide, again, it's sort of the same results on mbench, but also including the other colorful bars, the green and orange bar. This is instruction retired, run on Spike for load store double and plus the compressed encodings. This is compiled with O3 instead of OZ. The code size reduction is a little bit worse in that case, but you see that actually the reduction in instruction retired is quite nice. Really depends from workload to workload. You see the cubic benchmark just on the left actually doesn't benefit so much, but others have a bigger reduction even in the retired instructions than static code size reduction. You can see that, can take it as an indication of the performance improvement you would get, again, if you would have a 64-bit data interface. And also fetching less instructions usually means burning less power. This is the first chart showing also GCC results. The results are slightly lower than for LLVM. Honestly, we didn't put as much work into the GCC prototype as for LLVM, but it still shows that at least the obvious cases are being handled. It's a little bit of a different strategy than for LLVM. We're not touching the register allocation at all. This is also why you never see this actually lead to a code size increase. So it's really just picking the obvious cases, identifying the obvious cases, and putting the load double, store double instructions there. This is without ZCE, as we couldn't get that to compile. But we're still not applying that optimization to the prolog and epilogue. So that is still unchanged using load word, store word. In summary, so I introduced the ZLSD and Zclsd extensions. It's an extension which is, in the end, a bit situational. There are some scenarios, applications, where it shows great benefit. There are architectures where it's easy to implement. Other architectures might not want to implement that. And that's the good thing about RISC-V and about extensions. They're optional. So you can choose whether it helps you or not. If you do ZDNX, this is just really a game changer. Honestly, it takes the performance pretty close to the capital D extension, whereas without it, it's quite a bit worse. And we're expecting that for the P, the packed SIMD extension, you will see similar benefits because, I mean, it's sort of the same concept at the end of the day as ZDNX. Again, you will not just have static code size reduction. You will have performance improvements if you are able to load the 64-bit data word in one cycle. And that is true for many possible architectures. In particular, if you have an RV32 but dual issue core, there's good chances that you actually have a 64 or 232-bit data interfaces. So besides these great improvements of 15% plus where the workload really fits, even if it's just a generic workload that doesn't have any 64-bit data types in there, you still get 1 to 2% improvement. And I do expect that this might increase over time as the compiler matures, as maybe libraries get updated to support this extension. And I think, if anybody wants to look into this and contribute, I think this is a great opportunity. There's still quite some room, in my opinion. So, that concludes my talk. You can reach out to me if you want to say anything on the specification. Best case is actually you go on GitHub, check out the specification there. If you have questions, also create an issue. And that's how we can interact best.
All right, let's give him a round of applause. We have time for one quick question. If somebody at the back of the room has a question, they get priority because you sat in the back of the room. I'm going to make you ask the question. Robert, is your question quick?
Yes.
Okay, here we go.
You are quick.
If you implement D, then it doesn't make sense to do it. It's only Z. If you do ZLLD, that's with benefits.
So if you have the capital D extension, you can still do it. It also doesn't overlap with those encodings, but I mean, it depends on your workload. For example, if you have P and D, it might still make sense. I think that would be the most realistic scenario. But you cannot load those doubles into the D extension. But the D extension anyway has a floating point load double extension, which does this instruction, which does the same thing.
So like all good performance things, the answer is it depends. Yeah. Thank you, Christian. One last round of applause for Christian. Thank you very much.
Thanks.